As one of the first public key crypto systems, RSA, or Reverse Shamir-Alderman scheme, is used for secure data transmission. This public encryption method is based upon the difficulty of factoring the product of two large prime numbers. The individual publishes the public key based upon these two large prime numbers and auxiliary value. However, the prime numbers must be kept a secret in order to establish the public key. Thus, with these values, the RSA algorithm can be used to enable public key encryption and secure sensitive data, particularly when the data is sent over an insecure network like the internet. To begin with, let's ask the question, what is public key cryptography, or asymmetric cryptography? So, it's an encryption scheme that uses two mathematically related but not identical keys, a public key and a private key. Unlike symmetric key algorithms that rely on one key to both encrypt and decrypt, each key performs a unique function. The public key is used to encrypt, and the private key is used to decrypt. Likewise, it is infeasible to compute the private key based upon the public key. Because of this, public keys can be freely shared, allowing users an easy and convenient method for encrypting content and verifying digital signatures, whereas private keys can be kept secret, ensuring only the owners of the private keys can decrypt content and create digital signatures. So, with the advent of the World Wide Web in the 1990s, the use of public key cryptography changed. Computer performance had by then advanced to the point that the time for encryption and decryption operations was no longer an issue. Meanwhile, the killer application of online purchasing had exactly the characteristics that required public key cryptography. The web inherently didn't have essential control for security, so any merchant could go online without any prior security relationships with anyone else. And there was clearly a need to protect sensitive data, or else many consumers would not shop online if there was a risk that credit card numbers or order information might be intercepted by an eavesdropper or a third party. Thus, public key cryptography caught on rapidly.
RSA Encryption was created in 1977 by MIT researchers Ron Rivas, Adi Shamir, and Leonard Adelman over the course of a year. After they got drunk on Manischewitz wine during a Passover party, Rivas was too hungover to sleep, so he spent the night creating a working algorithm and nearly finished a formal report by dawn. In 2002, they received the ACM Turing Award for their significant contributions to cryptography. Rivas became an electrical engineering and computer science institute professor at MIT. He invented four prominent symmetric encryption methods, four cryptographic hash functions, and the three-ballot voting system, and founded the companies RSA Data Security, VeriSign, and Peppercoin. Shamir invented the FFS identification scheme and the Shamir secret sharing scheme. He discovered differential cryptanalysis, a method for cracking block ciphers, and wrote the Merkle-Hellman knapsack cryptosystem, visual cryptography, Toro factoring, and Twinkle factoring. Adelman created the field of DNA computing. He solved a 7-node instance of the Hamiltonian graph problem and is credited for publishing a paper documenting the first known instance of the successful use of DNA to compute an algorithm. In 1973, mathematician Clifford Cox created an equivalent algorithm for the British Government Communications Headquarters. However, running it on the computers of the time was expensive, so it was never employed. His algorithm was declassified in 1997, 10 years after the publication of the RSA paper. Now we'll go over how to create and deploy the RSA scheme. First, choose two distinct prime numbers P and Q. Since the RSA scheme is based on the difficulty of factoring the product of two large prime numbers, P and Q should be randomly chosen and differ in lengths by a few digits to make factoring harder. Now set n as P times Q. N is a modulus for the public and private keys. The bit length of the plaintext n must be less than the bit length of n to satisfy the condition 1 is less than n is less than n during encryption and decryption. So basically what that means is the longer your n is, the longer your message can be. On the right we'll be doing an example. If we set P as 11 and Q as 3, then n equals 11 times 3 is 33. We'll use Carmichael's totient function to define lambda of n. So lambda of n is the smallest positive integer m, where a to the m equals 1 mod n for every integer a between 1 and n that is coprime to n. In the context of the RSA scheme, we can set lambda of n as the least common multiple of p minus 1 and q minus 1. Lambda of n is kept private. So in our example, lambda 33 equals the least common multiple of 11 minus 1 is 3 minus 1, which is 20. Choose an integer e, which is greater than 1 but less than lambda of n, and is also coprime to lambda of n. In an RSA scheme, it's more efficient to choose a value where e equals 2x plus 1. So select a value from the list of prime numbers 3, 5, 17, 257, or 65537. In our example, we'll set e as 3, which is coprime to lambda 33, which is 20. Set e as a public key exponent. To calculate the private key exponent d, use the equation d is equal to e minus 1 mod lambda of n, which can be written as d times e equals 1 mod lambda of n. In our example, we can solve for d using 3 times d equals 1 mod 20, d equals 7. We set e equals 3 as a public key exponent and d equals 7 as a private key exponent. The public key is n comma e, and the private key is n comma d. In our example, that means our public key is 33 comma 3 and our private key is 33 comma 7. Now we can use our public key to encrypt the plaintext m into the ciphertext c equals m to the power of e mod n, where 1 is less than m is less than n. For example, we'll encrypt the plaintext m equals 7. The bit length of m equals 7 is less than the bit length of n equals 33, so RSA encryption is possible. We'll set the ciphertext c as 7 to the power 3 mod 33, which is 13. Now we can use the private key n comma d to decrypt the ciphertext c into the plaintext m equals c to the power of d mod n. In our example, c equals 13, so we can decrypt the ciphertext into plaintext m by solving for m equals 13 to the power 7 mod 33, which is 7. In our example, we use the public key 33, 3 to encrypt the plaintext m equals 7 into the ciphertext c equals 13. Then, we use a private key 33, 7 to decrypt the ciphertext c equals 13 into the plaintext m equals 7. RSA encryption, the individual releases the key n, e to the public, so the plaintext m can be encrypted into the ciphertext c. Then, using the private key n, d, the individual can decrypt the ciphertext c into the plaintext m, allowing for the secure transmission of messages. With high values of p, q, n, and e, the RSA scheme cannot be efficiently broken using conventional measures. In 1994, mathematician Peter Shor invented Shor's algorithm, which uses quantum computing to find the period of a modular function. Shor's algorithm can be used to break public key encryption methods like the RSA scheme, which was widely used at the time. Key encryption algorithms based on the RSA scheme are still used in most networks. However, the creation of the Shor's algorithm facilitated research on new cryptosystems that are secure for quantum computers. This field is collectively called post-quantum cryptography.
So in the case students don't grasp the mathematical concepts of the RSA scheme, the KID RSA scheme may be a modified yet simplified alternative of learning such concepts. So the KID RSA scheme was first proposed by Neil Koblitz, who purposely created this algorithm to teach kids the RSA scheme through easier terms, like simple arithmetic and modulus operations. He believed that cryptography has the potential to enrich mathematical education by providing a way to get students to discover certain key mathematical concepts and techniques on their own. Listed below are the 5 steps to practice the simplified cryptography of the RSA public key encryption. First, you choose 4 numbers, A, B, A1, and B1. Next, you set up 4 variables, M, E, D, and N, by using simple arithmetic with the 4 numbers established in step 1. After completing these steps, you should have now your public key, which is N and E, and your private key, which is D. With these 2 keys, you can first encrypt a plaintext P or any number using the formula C or ciphertext equals E times P mod N. And with your ciphertext after step 4, you can decipher it and revert it back to plaintext using the form P equals C times D mod N. So here's an example of the KIT RSA scheme. In step 1, we set A as 9, B as 11, A1 as 5, and B1 as 8. So in this chart right here, we have the equations listed for M, E, D, and N. And since we have the values in step 1, we can just plug it in, use simple arithmetic, and we get M as 98, E as 499, D as 795, and N as 4048. So with these values established, now we can move on to step 3. We know that public key is NE, which is 4048 and 499. And the private key is D, which is 795. So we can move on to step 4, which is encrypting plain text, and we set the plain text equal to 538. And with this formula, C equals E times P mod N, we can plug in the values, and eventually we get the ciphertext number as 1294. So with the ciphertext now, we can revert it back to plain text using the formula P equals C times D mod N. Eventually, we get that number to be 538, which is the original plain text. Mathematics has many more applications in computer security than just public key cryptography, of course. The design and analysis of more traditional encryption algorithms and one-way function also has a strong mathematical component, although perhaps not one so elegant as for public key cryptography. Intriguing mathematical introductions has also led to new types of cryptography, like identity-based encryption, a form of public key cryptography where one's name or email address itself becomes the public key, avoiding the need for a directory. More groundbreaking applications are likely to emerge over time as knowledgeable people continue to expand technological limits with regards to quantum key distribution and one-time pad, and to search what's concealed within mathematics. Who knows what other useful things we might find by exploring an otherwise obscure formula. Thank you.